All right, so this next set of topics is on simplifying trig expressions, which honestly is one of my favorite things to do. And I think the reason why is because it's kind of like putting together the pieces of a puzzle. And a lot of times you'll have a starting point and you'll have an ending point, and it's almost actually like a maze, and you're just trying to figure out how do I find my way from that beginning to that ending. Um, which is really just going to sort of press the buttons in your brain, kind of some creative thinking, and then also using all of your algebra skills that you've built up for forever. Why do we do it, or why is it such an important thing, and why do I, hope that you get a chance to kind of work through it right now? It gets used a ton in pre-calc and calc. Basically, to take, you're going to end up getting lots of trig expressions that are really gross, and if you can simplify them down to small, simple pieces, it makes all of the algebra and all the work you do from there on out a whole lot easier. The other thing that's really cool about these is that it's going to let us use our basic algebra skills that we've had for forever, try them out in a new context. And if you can do them with an entirely different context, that shows that you really understand those actual properties, which means you can apply them to just about anything. Okay, so if you can do them with trig, you can do them in any situation that you would ever need them. I'm going to try to follow along with this really awesome packet that I shared with you in this lesson. So it looks something like this. You should totally have it out while you're working on things, while you're going through examples. It's pretty amazing. Found it like a half a dozen years ago. It just does a great job of breaking down the strategies that we're going to use, showing step-by-step the examples, offering you a chance to do examples on your own, and then kind of describing the approach that you would use as well. But the very first thing we're going to do is we're going to go through what are known as the 8 fundamental identities. And what I've suggested to classes in the past when we've gotten to actually do this in class is I've suggested actually putting them on here, like, making yourself just a little box up in one of these corners somewhere on here, and putting these identities there so that you have them all in one place. And so that when you're working on this, you can just sort of pull out this packet and have them there. Because these 8 identities are basically like the little formulas that you can use to substitute stuff in. Okay, so like when you see tangent, and tangent by itself is not working, it's not simplifying down at all, you can substitute something in for tangent that might help you simplify something else. Okay, so we'll go through each of them. I'll kind of explain where some of them are coming from. Some of them you already know. 2 of them are what are known as the ratio identities. Tangent and cotangent are those 2. Tangent we actually already did back in chapter 13. Again, it's unfortunate there's this gap between there, but hopefully, some of the rust kind of knocks off of that eventually. Tangent is nothing more than sine divided by cosine. And so actually back in chapter 13, we actually proved this is true. So we were going through and we were doing the basic, or not the basic, but the special values chart, the special values chart over on the right side of that board. And we then did a little proof of why tangent equals sine over cosine. Okay, and we can do that proof again really quick here. Sine over cosine. Well, sine is just opposite over hypotenuse. Cosine is just adjacent over hypotenuse. Okay, when I'm dividing 2 fractions, that's the same as multiplying by the reciprocal. Let's get rid of that. And then you notice the h's cancel. And so I get opposite on the top over adjacent on the bottom. And we know from just basic experience, opposite over adjacent is just tangent. Okay, and so that was our proof. Okay, our proof that sine over cosine does equal tangent, because we were able to show it just through basic algebra steps that we already have. Okay, which makes it an identity. It makes it something that's always true. And what we just did here to prove this, to show this is what we're doing. Okay, so when I talk about simplifying trig expressions, that's what I'm talking about. Can you take something like sine over cosine, work through it, and realize that it's just tangent? Okay, and there are thousands of different identities. We're not ever going to try to memorize them all. I'm just giving you 8 basic ones to start with so you can just sort of learn how to do this. Okay, because it's a really important algebra skill and a really important calc skill as well. Okay, so if tangent is sine over cosine, that means cotangent is cosine over sine. And I know that because tangent and cotangent are just reciprocals of each other. And so I just flip it, and there you go. Okay, so those are the two ratio ones. The three reciprocal ones, we already know by definition from chapter 13. Cosecant is the reciprocals of sine. Okay, so anywhere I ever see cosecant, I can replace it with 1 over sine if I want to. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. Because we actually have two different formulas or two different identities that involve cotangent. Sometimes this one's more useful, sometimes that one's more useful. It's usually this one, but that's something that just comes with practice. Okay. And then the last three are what are known as the Pythagorean identities. Okay, the Pythagorean identities come from the Pythagorean theorem. Okay, so when we go back and we were working with unit circle stuff, so boom, boom, I had the unit circle, and on the unit circle, the radius is always 1. Okay. And if I take any point off of the unit circle, so like this point right here was the point root 3 over 2, 1/2. Any point on the unit circle, if I take the sine, which is the 1/2, squared, plus the cosine, which is root 3 over 2, squared, it should always end up equaling 1. Okay, so I'll show that for this example here. 1/2 squared is 1/4. Root 3 over 2 squared is 3 over 4, which equals 1. Okay. And so it's kind of a neat identity or a neat like little proof that you could end up doing. You don't have to do this. We don't do this by hand really ever. But it's just showing you that no matter what point I pick, okay, so whatever point I pick ever on a rotation, that is always going to equal 1 if I take sine squared plus cosine squared. Okay. So that's kind of neat. The other two are just rearrangements of this formula. Okay, so the Pythagorean ones, a lot of times, I mean, sometimes you see them and they look exactly like this, but sometimes you see them and they're rearranged. So maybe you don't have sine squared plus cosine squared. Maybe you have 1 minus sine squared. Okay, well, I can rearrange this equation. If I subtract the sine squared over here, I have 1 minus sine squared equal to cosine squared. This is the same formula, just rearranged. I move the sine squared over to this side. Okay, and I can do it, a whole bunch of different directions. Okay. Another thing that I can do is I can develop these two other ones based on this original one. Okay, so if I give you sine squared plus cosine squared equals 1. And I take the entire equation and I divide the whole thing by sine squared, which I can do, okay, as long as I do it to both sides of an equation, it doesn't really matter. Okay, so if I divide this whole side by sine squared and this whole side by sine squared, that's totally legal. Okay, again, it's balanced both sides. This will just be 1. Cosine divided by sine, well, that's an identity we just had right here, so we're already using one of these identities. Cosine divided by sine is just cotangent. So cosine squared divided by sine squared would just be cotangent squared because you'd have 2 of them. 1 plus cotangent squared. Okay. 1 over sine squared. Again, you're already using these identities to simplify this. 1 over sine is cosecant. So 1 over sine squared would be 2 of them. So that'd be cosecant squared. Okay. And so that one right here is that guy. Okay. And if I wanted to get this one right here, I would do the same exact thing I just did. I would just divide the problem by cosine squared instead. I take this whole equation divided by cosine squared, I would get this guy. And again, all the rearrangements you could ever imagine for these, also there. So what I always kind of hint to people is if you're trying to simplify something and you have sine squareds or cosine squareds or ones, if you have any combination of sine squareds, cosine squareds, ones, okay, or any of these guys and ones, it's Pythagorean. Okay, so if you have squareds or squareds and ones, it's coming from somewhere over here. You might have to do some rearranging and moving around, okay, but you're going to get it out of this. And so that manipulation takes a little practice, but again, it's really, really good algebra. And so those are our 8 fundamental identities that can be rearranged if we need to. We can see where they're coming from. We are actually, like, every time we do this, we're just doing a little algebra proof, okay, which, again, something in my brain at least really enjoys that because of the puzzle-like element of it. Like, can I take something and rearrange it and get the pieces to fit the way that I want? Okay. So the next ones, we will develop actually the strategies that we commonly use to take and do some of the simplifying. We actually already use some of them right here, but we'll break them down more specifically.